In this video tutorial, we will introduce the concept of electrochemistry and oxidation numbers. Oxidation-reduction reactions typically involve the transfer of electrons from one atom to another. If an atom has lost an electron, it is said to have been oxidized. On the other hand, if an atom has gained an electron, it is said to have been reduced. Please keep in mind that you cannot lose an electron without it being gained somewhere else, and vice versa, you cannot gain an electron until it's been lost somewhere else. As such, both reduction and oxidation reactions occur at the same time, and so they are commonly referred to as redox reactions. Looking at this example, we start off with a neutral zinc that turns into a positive cation, which means it has lost 2 electrons in the process and is said to have been oxidized. Copper, on the other hand, starts off as a positive cation, turning into a neutral atom of copper. And so during this process, it gains 2 electrons and is said to have been reduced. To help you remember all this, there is a lovely mnemonic called oil rig, where oxidation is loss of electrons and reduction is gain of electrons. Now, here's the confusing part. When zinc loses 2 electrons, we say it's been oxidized. Meanwhile, when copper is gaining 2 electrons, we say it's been reduced. But like I said before, you can't have one without the other. As soon as someone's being oxidized, someone else must be reduced. So when zinc is oxidized, we call it the reducing agent because it caused the copper to be reduced. Meanwhile, copper is the exact opposite. It was reduced, but we call it the oxidizing agent because it causes the zinc to be oxidized. Alright, so that's the confusing part. If you're oxidized, you're the reducing agent. If you're reduced, you're the oxidizing agent. So it's just the opposite. Let's take a look at the example down here. Pause the video and answer these questions. When you're ready, press play and we will take it up. Alright, looking at the iron, we go from neutral to a positive cation. The only way to become more positive is by losing the negative electrons. So iron has lost 3 electrons. According to our memory device, oil rig, oxidation is loss, reduction is gain. In this case, the iron is losing electrons, so it's being oxidized. And because iron was oxidized, that means it is the reducing agent because it causes the reduction half reaction. On the other hand, each hydrogen cation gains an electron to become a neutral hydrogen atom. Since reduction is gain, the hydrogen ion has been reduced, making it the oxidizing agent as it causes the oxidation half of the reaction. If you'll recall, back in grade 10 and grade 11 chemistry, you learned about single displacement reactions. In this particular reaction, solid iron is placed in an aqueous solution of copper 2 chloride. In so doing, the iron and copper swap places, turning the solid iron into an aqueous iron 3 plus ion, and the aqueous copper 2 plus ion into solid copper. On the other hand, placing a solid silver in an aqueous solution of copper 2 chloride results in no reaction occurring. The silver is unable to bump out the copper. To understand why that is, we had to consult the activity series of metals. Elements that are higher up on the activity series are more reactive, as they are more likely to lose their electrons and be oxidized. So looking back at our example, iron is higher than copper on the activity series, which makes it more reactive than copper, allowing it to spontaneously react. That is to say, it occurs without the need of additional energy input under standard conditions. On the other hand, silver is lower than copper on the activity series, so the silver is unable to bump out the copper. We call this a non-spontaneous reaction because additional energy will be required to make this reaction occur under standard conditions. Let's watch a quick animation to summarize what we have just learned.
If we place a piece of iron in a dilute solution of copper 2 chloride, the iron surface soon becomes covered by a layer of metallic copper, while the solution develops a yellow color. Iron replaces copper in the solution, which indicates that iron is more reactive than copper.
So once again, we have the solid iron swapping places with the aqueous copper 2 plus ion, resulting in the solid iron turning into the aqueous iron 3 plus ion, while the copper 2 plus ion becomes solid copper, covering the solid iron with a thin layer of solid copper. Now, you may notice that the chlorine is not included in this animation, and that is because chlorine is a spectator ion. As a reminder, spectator ions do not participate in the overall reaction. Chlorine started off as an aqueous ion, and it ends up as an aqueous ion. So nothing about it has changed. It was floating around as an aqueous ion, and it's still floating around as an aqueous ion. Meanwhile, the iron was solid initially, but then became an aqueous ion, while the copper was an aqueous ion initially, but then became solid copper in the end. Unfortunately, the animation still shows the copper as being in its ionic form when it should be in its solid form. So these should all be solid copper atoms and not copper 2+ ions. Don't let this animation confuse you. So again, ignore the chlorine. It is a spectator ion and does not participate in the overall net reaction.
If we now place a piece of silver in a dilute solution of copper chloride, despite prolonged observation, no changes can be seen and the solution remains clear. If any silver 1 chloride had formed, it would be visible in the form of a white precipitate. This time, the metal was not displaced from the solution because silver is less reactive than copper.
So once again, no reaction occurs when solid silver is placed in an aqueous solution of copper 2 chloride. Since the copper is higher up on the activity series than the silver, it is more reactive than the silver, and thus the silver is unable to switch places with it. And the copper 2+ ions remain floating around in solution, while the solid silver atoms remain solid. Now, the order of the elements in the activity series is based on the reduction potentials of these elements. So this list is experimentally derived. Using hydrogen as our reference point, our baseline, our starting point, scientists were able to measure the direction of electron flow into different materials, along with the change in voltage or the potential difference that accompanied the movement of these electrons. So when copper was reacted with hydrogen, it was found that electrons would move towards the copper, thereby reducing it and providing it with a positive voltage or potential difference. So all these elements, when reacted with hydrogen, would gain electrons and be reduced. By ranking them with increasing voltages, we can determine which elements are more strongly reduced, which ones are more likely to gain electrons, making them stronger oxidizing agents. So gold has a greater affinity or attraction for electrons than, say, platinum or silver or mercury. So once again, elements at the top of the activity series are most likely to be oxidized, so they will lose their electrons. So this makes them strong reducing agents because they will cause reduction in other elements. Meanwhile, elements at the bottom of the activity series tend to be reduced, as they are more likely to gain electrons. This in turn makes them strong oxidizing agents, as they will cause oxidation in other elements. Conversely, when zinc was reacted with hydrogen, the electron flow was found to move in the opposite direction, meaning zinc was being oxidized and losing electrons. So all of these elements, when reacted with hydrogen, would lose their electrons and become oxidized. Because the electron current is moving in the opposite direction, the voltage values are given a negative sign instead. So if you see a positive voltage value, that means that element is being reduced and is an oxidizing agent, with the larger voltage values indicating its relative strength. On the other hand, a negative voltage value indicates that the element is being oxidized. Again, the larger the magnitude of the voltage value, the more strongly the element is being oxidized and the stronger the reducing agent. Now, be careful, these reduction potential tables won't always be listed in this manner. So in this table, the oxidized elements are at the top and the reduced elements are at the bottom, but depending on the textbook or periodic table you are using, the elements being reduced might be at the top, while the elements being oxidized might be at the bottom. Just remember oil rig, where oxidation is loss, so you are losing electrons, and so we have a negative voltage, while reduction is gain, so your voltage values are positive instead. Alright, so be careful, these tables may be flipped, with negatives at the top, positives at the bottom, or positives at the top and negatives at the bottom. Just remember that positive is reduction, while negative is oxidation. In some cases, it can be helpful to think of redox reactions as being comparable to acid-base reactions. Where acids neutralize bases, oxidizing agents can neutralize reducing agents. While acids and bases typically involve the transfer of protons, redox reactions typically involve the transfer of electrons. We use the acronym Big ALE to help remind us that base is gain of the protons, while acid is loss of the protons. Meanwhile, we use the acronym Oil RIG to help remind us that in redox reactions, oxidation is loss of electrons, while reduction is gain of the electrons. Acid and base reactions can reach an equilibrium, while so can redox reactions. Previously, we had shown that a redox reaction between hydrogen and copper results in a flow of electrons from the hydrogen towards the copper. This process is accompanied by a voltage of positive 0.337 volts. So we can write this reaction out as hydrogen gas releasing electrons to produce hydrogen ions in solution. When these electrons flow to the other end, they cause the aqueous copper 2+ ions to become solid copper atoms. And this whole process causes a change of positive 0.337 volts. As this reaction proceeds forward, please note that this reaction is spontaneous, meaning that no additional energy beyond room temperature is required to move the reaction forward. However, as the reaction proceeds forward, the reactant concentration will decrease, which in turn reduces the forward reaction until finally we reach an equilibrium where the number of charges moving in this direction is equal to the number of charges moving in this direction. Without a net flow of electrons moving in one direction, the potential difference between these two sides becomes zero, which in turn drops the difference in voltages to zero as well. And that's why batteries eventually die and are no longer able to power your devices. As the electrons move spontaneously from the negative terminal to the positive terminal, the reactant concentration decreases while the product concentration increases. So the reaction starts off favoring the forward direction, but ends up reaching an equilibrium once the reactant concentration is too low. Now, if your battery is rechargeable, we can force the reaction to go in reverse. But this reaction is no longer spontaneous. If going in the forward direction had a positive voltage difference, we would need to add energy to the system to drive the reverse reaction, which is why we need to plug our rechargeable batteries into an external power source to drive the reverse reaction and recharge them. Alright, so going in the reverse direction is no longer spontaneous, and because the flow of charges is now in the opposite direction, we must also change the sign of the difference in voltage from positive 0.337 to negative 0.337. When it comes to acids and base strength, they are indicated by the magnitude of their Ka and Kb values, while similarly with redox reactions, the oxidizing and the reducing agent strength is indicated by the magnitude of their voltage potentials. So looking at our reduction potential table, gold has a magnitude of 1.50. Because it is a positive value, it is being reduced, so it's gaining electrons, which makes it an oxidizing agent. Because the magnitude of its reduction potential is higher than that of silver, gold is a stronger oxidizing agent than silver. Conversely, lithium has a higher magnitude than, say, aluminum, and because it's a negative potential difference, they are trying to lose electrons, so they're being oxidized. As such, lithium is a stronger reducing agent than aluminum. Now, when it comes to redox reactions, it is important for us to keep track of the movement of electrons. Where are they coming from and where are they going to? To help us with this task, we use oxidation numbers. These are numbers that are assigned to an element in a compound according to the rules shown below. By following these rules, we can more easily identify who is the reducing agent and who is the oxidizing agent in a redox reaction. Now, be aware, although an atom's oxidation number is often similar to its valence charge, this will not always be the case. Furthermore, it is important to note that oxidation numbers are not real. That is to say that they do not imply that the element in the compound acquires this charge. So if the oxidation number for nitrogen was a -3, it doesn't necessarily mean that it also has a valence charge of 3-. Quite often this is the case, but it does not always have to be true. Just remember that the oxidation number is a convenient number that we assign to an element based on the rules below to help us keep track of the movement of electrons. To help us differentiate between an oxidation number versus a valence charge number, when the sign is placed in front of the number, then we're talking about an oxidation number, so -3. But if the sign is placed behind the number, so a 3 minus, that indicates it's a valence charge number. Alright, so once again, oxidation numbers don't actually exist. They are numbers that we assign to an element based on the rules that we're going to be discussing in a few moments, in order to help us keep track of electron movement during a redox reaction. Alright, so what are these rules? Well, rule number 1, the oxidation number for any element in its pure natural state under standard conditions is 0. So if you recall, most elements on the periodic table under standard conditions will be solid. The only ones that exist as a gas at room temperature are the noble gases: nitrogen, oxygen, fluorine, chlorine, and hydrogen. So elements with a red font color are gases, while elements with a black font color are solids. There are only 2 elements that exist as a liquid under standard conditions, and they are mercury and bromine. You'll notice their font color is blue. So elements that are red are gases, elements that are black are solids, and elements that are blue are liquids. So if you see an element in its pure natural state under standard conditions, its oxidation number should be 0. Rule number 2, the oxidation number of a monatomic ion is equal to its charge. So remember, if the charge is after the number, that's a valence charge. If the charge is before the number, that is its oxidation number. So in this case, the copper 2+ ion has a valence charge of 2+. As such, its oxidation number is +2. For chlorine, its valence charge number is 1-, thus its oxidation number is -1. For the iron 3+ ion, its oxidation number is +3. For rule number 3, the oxidation number of oxygen is almost always going to be -2. However, when you're dealing with peroxides, the oxidation number is a -1. So down here we have hydrogen peroxide, where the prefix per means that there is 1 extra oxygen than is normally there. So normally with H2O, the valence charge on hydrogen would be a 1+, while the valence charge on oxygen is a 2-. But when we say peroxide, it means that there is an extra O that normally isn't there. As such, the valence charge must be a 1- in order for this to balance out, resulting in an oxidation number of -1 instead. Rule number 4 deals with hydrogen. Normally hydrogen has an oxidation number of 1. If the hydrogen is bonded to a nonmetal or an anion, then it is a +1 oxidation number. If the hydrogen is bonded to a metal or a cation, then its oxidation number is a -1 instead. For rule number 5, the oxidation number of fluorine is always -1. When it comes to the other halogens, they too will typically have a -1 oxidation number. However, there will be some instances where that won't be true, like when they form compounds with oxygen or each other. This will make more sense when we introduce rule number 6. That being said, alkali metals and alkaline earth metals typically have an oxidation number of +1 and +2 respectively. Looking at sodium chloride, sodium being an alkali metal should have an oxidation number +1. Whoops, I wrote 1+. It should be a +1. Same thing with magnesium, because it's an alkaline earth metal, it should have oxidation number +2. So, whoops, +2. And then chlorine and fluorine being halogens should have a -1 oxidation number. With rule number 6, the sum of the oxidation numbers in a neutral molecule should be 0, while the sum of oxidation numbers in a charged molecule is the charge of that molecule. So you may have to do a little bit of detective work to determine the oxidation number of some elements. Because sodium chloride has no overall net charge, the oxidation number for each element should add up to 0. And it does. Sodium being an alkali metal has a +1 oxidation number, while chlorine as a halogen has a -1 oxidation number. +1 added to a -1 adds up to a 0. Oxygen, as we mentioned earlier, is almost always a -2 unless it's a peroxide. So I'm just going to write down -2. But because there's 4 of these oxygens, -2 times 4 equals -8. Now, we have no rules concerning phosphorus specifically, so we don't know its oxidation number right from the start. Instead, we're going to use rule number 6 to help us solve for the oxidation number of phosphorus. Since the overall charge of this phosphate ion is 3-, I know that the sum of these oxidation numbers must add up to -3. So -8 plus a mystery number equals -3, and the only number that can make this statement true is if phosphorus is a +5 oxidation number. Looking at this example, we know that oxygen is almost always a -2 unless it's a peroxide. So I'm going to write -2 at the top, and that's all due to rule number 3. And because there are 3 oxygens, 3 times -2 equals -6. Now, according to rule number 6, the sum of these oxidation numbers must add up to the valence charge. So this must all add up to -1. And the only way for this equation to be true is if chlorine has an oxidation number of +5. So that's what I meant in rule number 5 when we said that halogens are typically -1. So chlorine, being a halogen, should normally have an oxidation number of -1, except in instances when they form compounds with oxygen or each other. So here chlorine has formed a compound with oxygen, so we must use rule number 6 and some detective work to determine what the oxidation number is for chlorine in this case. So that's what we meant initially when I said that oxidation numbers don't actually exist. They are just made-up values that we assign to an element to help us keep track of the electron movement. So chlorine doesn't actually have a 5+ valence charge. This oxidation number is assigned based on these 6 rules. Sometimes they'll match up with their valence charges, and sometimes they won't. Alright, using the rules that we just learned, try and identify the oxidation number for each element in the examples below. Press pause. When you're ready, press play, and we will take up the answer. So in the first example, we've got potassium. Because potassium is a group 1 element, and according to rule number 5, alkali metals all have an oxidation number of +1. Potassium must have an oxidation number of +1. According to rule number 3, oxygen always has an oxidation number of -2 unless it's a peroxide. And since this is not a peroxide, the oxidation number for this oxygen is a -2. Now, there are no specific rules for the oxidation number of manganese, so we will use rule number 6 to try to identify the ON value for Mn. So we have an oxidation number of +1 for the potassium. We don't know the oxidation number for manganese. And since we have 4 oxygens, each with an oxidation number of -2, so -2 times 4 equals -8. And since this molecule has no overall charge, this all must add up to 0. So the only number that can make this equation correct is if manganese had an ON value of +7. In the next example, we don't know the ON value for chromium, but according to rule 3, the oxidation number for oxygen is -2. So -2 times 4 equals -8. And according to rule number 6, the sum of oxidation numbers in a charged molecule is the charge of the molecule itself. Since the charge of the molecule is 2-, this all must add up to -2. So the only number that can make this equation correct is if chromium had an ON value of +6. In our next example, we're going to look for the oxidation number for hydrogen. According to rule number 4, the ON value for hydrogen is always a 1. But if the hydrogen is bonded to a metal or a cation, it's going to be a -1. In this example, the hydrogen is bonded to a metal cation, so its ON value is -1. Since there is no overall charge for this compound, the ON values must add up to 0, which means calcium must be a +2 oxidation number. This matches up with rule number 5, where they say alkaline earth metals, or group 2 elements, have an ON value of +2, which matches up over here because calcium is an alkaline earth metal. In our next example, oxygen is almost always a -2. -2 times 10 is equal to -20. Since this molecule has no overall net charge, the oxidation numbers must all add up to 0. Since there are 4 of these phosphorus atoms, only an oxidation number of +5 can make this equation true. So phosphorus has an oxidation number of +5 in this situation. Now this next example is a little interesting. Again, the ON value for oxygen is almost always -2. -2 times 4 is equal to -8. Because there's no overall charge, the oxidation numbers must add up to 0. There are 3 of these irons, so the only oxidation number that can make this equation correct would be a +8/3. So this iron has an oxidation number of 8/3. Again, oxidation numbers are not real in the sense that 8/3 is not the valence charge of the iron. Instead, this oxidation number is a number that we have assigned to the iron to help us keep track of electron movements, which you will see in our next video on balancing redox reactions. On to the next example. Oxygen has a -2 oxidation number because there are 4 of them. That gives us -8. According to rule 6, all of these oxidation numbers should add up to the charge, which is -2. So the only number that can make this equation correct is if sulfur has a +6 oxidation number. In our final example, again, oxygen has an ON value of -2. -2 times 3 is -6. There are 2 of these nitrogens and there's no overall charge. So when we try to add it all up, the only number that can make this equation correct is if nitrogen had a +3 oxidation number. Alrighty, so learning these oxidation number rules will help us to keep track of electron movement, which will be important in our next video tutorial on balancing redox reactions.